We begin the program today with a keynote address from Professor Michael Franz from the University of California, Irvine. The ACM has named Michael the recipient of the 2020 ACM Chuck Thacker Breakthrough in Computing Award for the development of just-in-time compilation techniques that enable fast and feature-rich web services on the internet. More colloquially, that means that if you've ever used a web browser to check your email or view a video or do anything with social media or anything that uses JavaScript, then under the hood you've been using things pioneered by Michael. The ACM Chuck Thacker Breakthrough in Computing Award recognizes individuals or groups who have made surprising, disruptive, or leapfrog contributions to computing ideas or technologies. The award is accompanied by a $100,000 cash prize and the opportunity to deliver the ACM Breakthrough Lecture at an ACM conference. And we are, of course, honored to have Michael select ASPLOS'22 as the venue for his lecture. Professor Michael Franz received a Doctor of Technical Sciences degree from ETH Zurich, right here in Switzerland, so quite fitting as well. He then joined University of California, Irvine, as an assistant professor in 1996, where he now holds the title of Chancellor's Professor in the Donald Brent School of Information and Computer Sciences. Throughout his tenure, Michael has graduated 28 PhD students, has published more than 150 papers, and was awarded 5 US patents. He is a fellow of the ACM, the IEEE. He is a recipient of the Fulbright Scholarship, the NSF Career Award, the IEEE Computer Society's Technical Achievement Award, the UCI Applied Innovation Innovator of the Year Award, the Humboldt Research Award, and now, of course, the ACM Chuck Thacker Breakthrough in Computing Award. So with that, please join me in congratulating Michael and welcome him to the stage.
Thank you very much for the introduction. So when you hear the word breakthrough, you somehow think that this is something that happened like in one day. You were taking a shower, had a great idea, and the next day you had the breakthrough. And what I'm going to tell you today is that this is a much longer process, and sometimes it also just relied on being in this right place at the right time. So let me start quickly talking about how far back this actually started. So back in 1989, I was actually already an undergraduate at ETH, and I got an offer to be a PhD student in the group of Niklas Wirth, who some of you may know. He's a Turing Award winner, the inventor of Pascal. And of course, he wasn't Niklas Wirth, he was Professor Wirth, because we're in Switzerland. And so I didn't actually call him by his first name until I myself was a professor. And there was this whole research group doing compilers, and this is me in my first office. These are not bars on the window. This is just the blinds that look like it. And at the time, all of the people in Wirth's group were basically porting Wirth's then new programming language, Oberon, and the Oberon system that came with it to various architectures. So each of the PhD students was doing a version of Oberon for some other target architecture. And mine was actually the Macintosh running on the 68,000 Motorola processor. And so there were all these versions of Oberon being created. And then I read this paper, and that is actually the best version of the paper I could find. And that was a paper by Deutsch and Schiffman talking about the original Smalltalk implementation. And they used just-in-time code generation to make it run faster. And I was totally hooked on this idea. And in the context of Oberon, where you actually had pretty much just the same source code base, except for some very, very slim APIs at the bottom, it would have been a great idea to use this just-in-time code generation for all the different versions of Oberon. And the problem was that even though we had really fast compilers for the time, they were not fast enough to really do this. And so the first big idea that my first publication on this, which I believe was in 1991, was later the topic of my dissertation, was that if you could come up with an intermediate representation, a wire format, that was so much denser than object code that you would have to read less from disk when you loaded the program, then you might be able to actually use those cycles you saved, not having to read large object files, by just generating the code on the fly. And I took this to Wirt, and he said, "May, whatever, yeah, why not? Just try it." You know, and so he let me do it. And so the interesting thing was that, you know, the observation was, of course, that processor speeds were growing exponentially at the time. This was, you know, Moore's law was still working. Everything was great. And storage speeds were growing only linearly. And I later actually plotted this in a later paper. I was doing this on Mac, right? So these were actually the speeds of, you know, the disk index and the CPU index. You could see that was really happening. And so when I defended my thesis, my just-in-time solution was just a little bit slower than just reading it from disk. And just a year later, the two curves had actually crossed. And using the exact same software on newer hardware, it was actually quicker to generate the code on the fly rather than reading stuff from disk. And so what was the main idea? The main idea was compression, right? Compression of the IR and then just generating the code on the fly. And so the thing that I actually came up with was this concept of adaptive compression of syntax trees. So the idea was, you know, I have a shared vocabulary between sender and receiver, and the sender is, in this case, the compiler. The receiver is the just-in-time code generator in the loader of the system. And so I have a program that has 3 integer variables, and there's some assignments. And you start off by just sending, these are the variables in my program. And both the sender and the receiver then construct permutations on what's just been sent here. So I have use of the variables and assignment to the variable, which are the indices, you know, the dictionary entries that I'm creating. And now I have a language that the two can communicate with that keeps evolving, right? So I have an assignment, I plus j is assigned to I, and so these, if you just think these are, you know, 1, 2, 3, 4, 5, so index number 5 is assignment to I, and I have the sum of I and j. And after you've transmitted this, you actually add additional things to the vocabulary. And in this case, you would add not just the subtrees you've just seen in the syntax tree, but you would even speculatively add a few permutations in the expectation that they might also occur. So what you're doing is you lose a few bits, you know, of encoding, but with a chance that you might actually profit enormously if that speculatively added thing to the dictionary will occur later. And that's what actually was going to happen here, right? So I have the I plus and so as you see, I can now encode this sequence, and I keep growing the dictionary. And so in 1994, I defended my PhD dissertation. I did get the PhD. And, you know, so that's the name of the dissertation. That is actually taken on, you can see in the background, that's actually just before I start my defense, that photo. And actually, you know, we had this idea of what you call dog fooding today, right? Eat your own dog food. So I actually wrote my dissertation on a system that was dynamically compiled every morning when I started it. So that was kind of a measure of pride. And so the strange thing is that when I went on the job market afterwards, people were not receptive to this idea, right? So I went to some places where they were big in compiler construction, and I got things like, young man, the whole concept of a compiler is based on the idea that, you know, you invest the effort into compilation just once, and then you profit from the invested time over a long period where the code is just executed. And the idea of doing it every time was just totally outlandish. So people did not buy it, and people were almost hostile to the idea. And then something strange happened. Then in 1996, when I was already at my first job in Irvine, all of a sudden the Sun announced Java. And from that time on, because there was this big push by this big company, everyone in retrospect thought that I had been working on Java, of course, right? So the title of my dissertation was related to Java, and of course this was a great idea because everyone was doing it. And so the system that we built, so my first PhD student and I actually kept doing this for a little while, and you can see one of the papers here. So it actually became the standard distribution format for Oberon for a few platforms, but because Java sort of swept everything aside, nobody really cared anymore, right? So Oberon kind of just died a slow death, and that was it. So we got into the Java years, and everyone is doing it, and the funny thing is, this applet thing really never happened as the world believed it was going to be happening. So there were huge numbers of people who all of a sudden were developing just-in-time compilers. And so, I kept doing it. And you can see I worked on continuous feedback optimizations. And everyone was assuming that I was part of the Java crowd from the very beginning. But at the back of my mind, I was really not that happy with Java, right? So, because Java is really a quite low level, and there's this huge semantic gap between the Java virtual machine and the Java source code language, which necessitates this whole thing of doing Java bytecode verification. And so, in particular, in Java, you have this thing where you have this rather simple compiler where you compile Java down to the JVM bytecode thing. And then on almost all platforms today, we spend an inordinate amount of additional work first lifting the low-level Java bytecode back up to something that compilers really want to have as the input, and then eventually lowering. So in fact, this is actually even worse than shipping, compressed syntax trees, for example, right? Because all this work lowering it back up is really time that you have to spend, every time you run the program. And the second problem with this, of course, is that Java bytecode verification is complicated. And so the problem with Java is that Java has stack frames, local variables, and so on, and they are dynamically typed, right? So, and you must prevent, for example, an integer being converted into a pointer, and so you must not be able to push an integer onto the stack and then jump somewhere where a pointer is read from the stack, because that would be an implicit conversion. And so the Java has this bytecode verifier, and the bytecode verifier, there's really only one bytecode verifier in the original Java implementation. That was the Sun one, and people just got the source code and used the Sun one because that was the official way of doing Java bytecode verification. And we actually showed that you could very easily construct a program that had worst-case runtime behavior in this particular way of the iterative data flow that the Java bytecode verifier was constructing. And so you had a program that will verify eventually, but takes enormously long to do this. And so this is where you can see the operation. This is just the one variable, which initially is initialized as an integer, stored as an integer. And then in the end, when you iterate, you find, oh, there's actually a pointer. And every time you do this, you trigger another iteration. And after many, many iterations, you compute the stack state, because now you have an integer and a pointer, and then so that becomes top. And so this is the worst case data flow, and you can see this was 2005. time to verify a single method with worst case data flow, and you can see it goes up exponentially. And it's even worse because Java had this, or has this thing called a jar, which is a compressed archive. So you can have very, very, very small jars that take forever to verify. And so 15 minutes for a 3.5 kilobyte jar file on then a top range desktop computer. And eventually it will verify. It just takes that long until it does. And so later versions of the bytecode format actually includes what they call stack maps, which is basically the computed fixed points of the data flow equations. That's the state of the stack at every basic block entry. So you don't have to do the iterative analysis. So for a while, I tried really, really, really hard to get rid of the JVM. So we came up with all these interesting formats for SSA-based mobile code formats, and I'll talk about some others. So, even got published in PLDI at Transactions and Architecture and Code Optimization. So we got some traction with it, but nobody was really interested in throwing out the JVM and using something else. And I went further on. So the first idea that came with Java was this idea that you actually, the zeroth idea is just ship binary code with a certificate that it's trusted. The first idea then that follows is look at the code itself and decide whether it's going to do something bad or not. That's what Java does. The second idea is proof-carrying code, which came just a year later, where you ship a proof in addition to the mobile code, and the proof makes it easier to verify that it won't do anything bad. So stack maps are essentially proofs, some kind of a proof in this case. And so we worked on something called inherently safe code. And the idea is how about inventing a transportation format in which bad programs cannot actually be expressed. Right? So this is like in George Orwell's 1984, there's a Ministry of Truth that has a language called Newspeak that is derived from English by removing all the words that can be used to think evolutionary thought. And the general idea is even older. It's Ludwig Wittgenstein thinking about whether or not there is something like a Gödelization of thought and other unthinkable thoughts. So how would you do this, right? So you want a class of machine-independent code representations in which safety is obtained by construction, and you want to actually provide the identical safety guarantees that the Java virtual machine did, that at least at the time that was what we were trying to do. And so we don't know what an incoming program does, but we know it's not going to be doing anything bad for any definition of bad that we can encode in the type system. And so we came up with these interesting things saying, okay, so for example, in Java we have assignment compatibility, that you can assign a subtype to a variable that's statically declared as a supertype, but not the opposite. And so if we look at, this program has 4 variables, and these are the useful assignments, these are illegal assignments, and then we have pointless assignments where we have a variable being assigned to itself. So what if we actually just enumerate all the assignments that are actually useful, and we only ship the index, then nobody is able to express an illegal assignment. Okay? And the beneficial side effect is compactness, because I was always interested in compactness. Right? You need to express 1 out of 8 choices rather than out of 16 choices. And the interesting thing is that such encodings can also be used to encode things that are compiler-derived information. So, for example, escape analysis. And you probably all know that one of the things that compilers do quite well in many languages is escape analysis. So if I have an object that is created inside of a function, but that doesn't ever get assigned to a global variable, then I can allocate that object on the stack, because and so I don't have to do the expensive heap allocation garbage collection. I just collect it when the stack frame is removed. And so that significantly can help performance in Java. The analysis is difficult, but the results of the analysis are actually easy to verify. So, for example, what we could do is we could augment the type system of our intermediate representation with captured versus not captured, and we can make that part of the encoding itself. So I have captured objects, I have other objects, and then I actually use exactly the same. This is exactly the same slide as before, just now that I have these other assignments, right? You're not allowed to assign a captured reference to a general variable, because through that it might escape, and you can encode this efficiently. So that's great, and we showed that by doing this. This is slightly different from what a general compiler would do. We don't actually annotate allocation sites, but we annotate variables that are guaranteed to be holding only captured variables. But you're getting this for free, right? You're doing this once at the code producer, and the code consumer doesn't have to do the analysis. So this is still beneficial, even if it doesn't capture all the same values. So this was quite useful. And the next question, of course, becomes, how do you actually enumerate all the possibilities that are there so that you can, if in the end only have the index that you need to communicate to the other side, right? So that's, I said all the time, I'm enumerating all the legal things, but obviously, how do I start off? I have a program, what are all the legal things in the program? And so we came up with this slightly cool solution based on arithmetic coding. So what is going to happen is we are going to map any program onto an interval, and any real number that falls into the interval is going to represent the program. Okay? And the idea is that we can actually do this as we go along, incrementally, quite easily, by just going down the syntax tree. So let me explain. So here I have a program that I want to encode, and I know that in my grammar, a statement can be an assignment, an if statement, a while statement, and so on, and I have probabilities, and these probabilities can either be static, computed in advance, because I know that for a large corpus of programs, these are the probabilities, or I can even do it adaptively and can keep adjusting them. And so I have an assignment, and let's say the assignment is the 70% most probable. And so what I'm going to do is I'm going to shrink my interval from being from 0 to 1 to 0 to 0.7. And then, so I've opened my choice only a very little bit, and then I'm going to again enumerate my choices in the next step. So the target can be a local variable, a global variable, or something more complicated like an array index or something like that. And so let's say it's a local variable which has a probability of 90. So now my interval has shrunk to between 0 and 0.9 times 0.7. And then now I'm getting to which local variable is it. So I have I, j, and k, and let's say it's j. And so I'm going to start at 0.7 times 0.9 times 0.3, and then end at 2 times that. And so the final interval is going to be enclosed in this range. So any bit sequence that represents a real number that starts in this interval is going to be a program that starts with an assignment to j. And now I'm going to output a single bit of the final encoding and then scale everything by 2. So I've used 1 bit so far to encode an assignment, a program that starts with an assignment to j. And then the next step is, what is the source? And the source is, in this case, another local variable. And so that is another 2 bits. So with 3 bits, I have encoded this. So this is really cool. And it turns out that this way of at least for Java, is actually more compact than even specialized compression algorithms that were developed for Java ahead of time. And it has the cool thing that you don't have to validate anything, right? So you can take a picture of the Mona Lisa, and it's going to be a valid program. We don't know what it does, but it's not going to do anything bad under any definition of bad that we have put into this encoding. So, so I thought I was in the business of developing wire formats. And lots of people thought that. And most importantly, people at Mozilla thought this. And so I was invited to Mozilla, and I went there a few times. And so Mozilla were the people who were making the Firefox browser. And the gentleman is Brendan Eich, who was at the time the CTO of Mozilla, but he's also the inventor of JavaScript. And he had this beautiful language, JavaScript, and he did not have a wire format. JavaScript at the time was sent around as source code, and everyone thought that was stupid. Everyone thought that you need a wire format because that's what people do. And so I was the wire format guy, and so I was a professor with a solution, and we were professors with solutions, right? So, so I went there and we talked, and and I went in thinking JavaScript is this little scripting language, right? And the funny thing is that everyone in academia thought JavaScript was this little scripting language. And there was no major web browser in the world that had a JIT for JavaScript. And in fact, as far as I know, there was nobody working on a JIT for JavaScript except for the people at Google who were secretly developing Chrome, but weren't telling anyone about this. So V8 and Chrome were a closely guarded secret at the time. So, and everyone was working on Java. So there were lots and lots of Java JITs. And this crazy thing was that when something moved in the browser, or when you had things like maps that could be panned, or even I think Gmail may have already been around, people thought that was Java. Whenever people had been so brainwashed into believing when something moves in the browser, it must be Java, a Java applet. And in fact, there were no Java applets. Nobody was writing Java applets. People were actually writing JavaScript even then. And nobody knew. And Brendan was really saying, well, he said the amount of JavaScript processed by a typical browser in a single day is orders of magnitude larger than the largest Java applet ever seen by such a browser. And I went, whoa, so why are there no JITs? And everyone said, I don't know. And nobody was interested in doing a JIT. So the crazy thing was that it became evident quite soon that doing a wire format for JavaScript was probably not in the interest of JavaScript. And later on, I actually came to understand that probably because of the semantic gap, it might not really be useful at all. It's actually not a bad idea to ship source code. So I totally got over my fixation on wire formats. But since I was already there, and Brandon kept telling me about all these great amounts of JavaScript that were sloshing around the system, I said, well, why don't we build a JIT? And nobody felt an urgency for having a JIT, because nobody was doing it, and so I said, well, I have this new way of building JITs. That we actually originally built for embedded processors doing Java, but why don't we try this on JavaScript? And so Brendan said, okay. And Mozilla actually, committed resources. There were people at Mozilla that were implementing this. And I now believe that, if anyone had thought this was important, they would never have allowed us to build a JIT using this totally unproven, never before used technology for building the JIT. But because it didn't matter, yeah, why not? So our original thing was this JIT called HotPath VM that we had built for Java, and it had pretty good numbers. So it was about 350 times faster than Sun's Hotspot compiler. It generated only a 30th of the code, so it narrowed down on only really the hot code and didn't generate so much cold code because Hotspot generated code method by method. The compiler was really, really small, right? It was written by 2 people, and the total memory footprint was only about 1/7 of Hotspot. So that was good. And at the time, Firefox didn't really want to have some gigantic compiler attached to it. So this was good, and so we did it. And when we were done, so this is August 23rd, 2008. This was Brendan's original post on the Mozilla wiki, where he said, we now have this new compiler, and the first results are really good. And everyone was happy and thought, okay, this is good. And then just 3 or 4 days later, all of a sudden, there was this comic leaked on the web, and some of you may remember this. So Google didn't actually do a press release. Someone leaked the comic that they had written for this. And here you can see, wouldn't it be great then to start from scratch and design something based on the needs of today's web application and today's users? So, they were not being shy about this, to say the least. So the good news was that Firefox actually had something almost shovel-ready, and without it, probably Chrome would have taken over the world much sooner than it may be doing now. And there was a slight snag, and the slight snag was that we had actually filed a patent application on our main invention in this, and the patent eventually was granted. But of course, Firefox doesn't charge any money, and out of philosophical reasons, Mozilla is actually fundamentally opposed to software patents. So we had an interesting Memorial Day conference call with lots of parties involved. And in the end, it was agreed that there was not going to be a license, but there was actually going to be a covenant not to sue, which probably is almost the same as a license by any other name. But we really have to thank the University of California to be so enlightened as to say, yeah, you can have this without paying any royalties, because otherwise it would have hit a major roadblock, right? So when you are in academia, vanity patents may not be the most useful thing if you, in the end, it's going to prevent you from bringing things into practice. So let's get into what was actually the invention. So for 3 decades, existing compilers basically worked like this, right? So you have a program, and you build a model of the program, which is a control flow graph, and then you somehow walk the model and generate code in the process. And there's lots of problems with this. Well, first of all, there's hot code and cold code, and in fact, you actually have very little hot code typically. And the other problem is that the control flow graph algorithms are very complex, and if you want to do global optimization, you actually need to really build a control flow graph for everything. And you all know this. Most code is cold. And so the idea that we had is, well, how about compiling only the loops in the program, right? And so we were going to integrate with the existing interpreter, but you could also integrate with a quick and dirty baseline compiler. And today, of course, it's standard that just-in-time systems even have multiple levels of compilation, and depending on how hot something is, you keep kicking up to higher levels and higher levels of compilation. But at that time, that wasn't so. And so you discover loops by interpreting the program, and And then you make a bet that the next time you are going through the same loop, it's going to do exactly the same thing as when you looked. And if we lose the bet, we bail out to the interpreter, and we can make a new bet at that point. Now, at the time, there was actually a system already, the absolutely great Dynamo system that was done by Bala, Düsterwald, and Banerjee for HP RISC. And they invented this idea that you discover loops by looking only at backward branches. And so they had the idea that if every program location that is reachable by a backward branch has a counter attached to it, and you just have a saturating counter, when it overflows, you've discovered a loop, or even a hot loop. And then you start following the flow of execution forward until you reach that point again, and then now you've traced the loop. And so what they actually did is they tried to accelerate PA RISC running on PA RISC. So the actual hardware platform that they were running on was the exact same hardware architecture than they were dynamically jigging for, and yet they were able to squeeze out a performance improvement by doing instruction scheduling and some limited inlining on the code sequence they saw. But they stayed with the traditional concept of a trace, where every basic block belongs to exactly one trace. And so you had these compiled bits, and you would stitch them together, and eventually, hopefully, you would run almost entirely inside the code cache. Now, and the important thing is they didn't optimize the way stack frames. So if you had a call and a return, you would still build the stack frame, and you would have to get rid of it later. And so the key invention that we had, what the patent is basically on, is this idea that our compiled code has copy in, copy out semantics. And what we're actually doing is we're taking all the state of the interpreter that we need in the compiled code, and we explicitly move it into our compiled code. And those things become SSA definitions. And then we convert the whole thing into static single assignment form. And at the end, we have different bailout points. On every path leaving the interpreter, we copy back the modified things to the interpreter state. So we don't actually modify directly the state of the interpreter. And that's the key here. And because there's only one loop that we're optimizing, free node placement is actually trivial. And so I don't know, hopefully most of you know static single assignment forms, so almost all compilers use that today. So you use static single assignment form to answer the age-old question. You have two expressions, and the question is, are they computing the same value? And of course, they compute the same value if, first of all, neither of the parameters has been modified along the way, and also every path from the first computation, every path to the second computation goes to the first. And so what compilers have used for a long time is this thing called static single assignment form, where you have a phi function, and phi has this weird semantics. The result of phi is the first parameter if you came from the left, and the second parameter if you came from the right. And you should probably read up on this if you haven't heard this, because it's one of the greatest ideas in compiler construction. So what we're doing is, so we have an original program, and what we're doing is, first of all, we're looking at all the values that are actually needed inside the compiled code after we've traced, and then we compile this into IR. And we generate the phi functions for all the values that are actually modified in the loop. And as part of this, we can actually trivially detect loop invariance now, because in SSA form, if something does not have a phi function, it must be loop invariant, so we can hoist it above the loop. And so the whole compiler is super, super, super fast. It has 2 linear passes on this intermediate representation. So the first pass does all the things that are up there, and the second pass does all these other things going backwards. And as an added bonus, you can even do dead code elimination in the process, right? And so so I have an example, right? So this is a code, and in this code I have a while loop, and I have an if statement. And so what happens is that at some point I'm going to count how often a target is reached via a backward branch, and so that loop header there is going to be eventually go hot enough that we kick in the trace recorder. And what happens is that we're going to follow exactly one path, and hopefully we're going to get back to the same loop header. And there's all kinds of bailout conditions where we have to decide, okay, we're not getting back to the loop. So the hope here is that the one time we're looking, the loop is going to do something typical. And so now we've traced this, and what we're going to do is we are now going to compile this into the thing on the right, and the two bailouts are paths that leave the compiled code, right? And as you can imagine, because we have these write-back semantics for every path to a bailout, we can actually compute exactly what values need to be written back. So those are stubs that are generated along the bailout paths. And we can then optimize all these things with each other because now we know that's a loop. And we can even hoist things above the loop. And so if we have something, and I don't know if you can see this, so the D was originally not seen, right? This compiler does never at any time have a global view of control flow. So we only are discovering control flow as we go along. And after a while, D gets lukewarm. It's not as hot as the other part of the loop, but we notice this because the bailout point here also has a counter attached to it, and it keeps getting hotter. And so when that happens, we just kick in the compiler again, and we also record that path, and then we compile it as well. And as you can see here, what we're doing is we actually have tail duplication here. We are incrementally adding, so we actually keep copying all those basic blocks for every loop. So every one of these loop bodies is added independently of each other. And now it gets interesting. So now I have a loop that actually contains a call, and this is a method dispatch. And what I'm going to be doing is I'm actually going to trace through the call completely. And I'm going to compile this into the thing on the right, where the method dispatch is actually going to be compiled into a comparison. Am I actually calling the same method as the time that I recorded this? And if yes, I bail out, then I have to do the dispatch again. And on the path where it is the exact same receiver type, I just keep going. So now I've inlined the method call completely into my loop. And the interesting thing here is that the bailout that I have at the bottom, the dark blue one, that's a bailout from inside of a method whose stack frame was never actually created in our compiled code. So I will have to, at that bailout point, I will have to construct that stack frame on the fly. So I had some discussions later with some of the Dynamo people, and they actually thought about this, and they thought that was going to be too difficult to do that, to generate the removed stack frames on the fly in these cases. And it turns out that using this SSA-based representation, you can actually do this very efficiently. And so when you have object-oriented programs that have multiple receivers, right? So this method can dispatch to that implementation for that class and to a different one from a different class. This gets compiled into, essentially you're going to have a ladder, and you're going to have the different receiver types in exactly the frequency in which they typically appear at runtime. And you're going to keep comparing, and you're going to have all the different implementations lined up right there. And the cool thing, of course, about this is that's the key to efficiently implementing dynamically typed programming languages, right? In dynamically typed programming languages, you don't have explicit classes, but you have something very similar called hidden classes. So what you typically do is you create a state machine behind the scenes, and every time that slots are added to to an object, you just move it in the state machine to a shape that has these slots. So you have exactly the equivalent to the class code here. And now, if you have things like integers or other primitive data types, and you know that it's an integer, then you can completely do regular arithmetic, and you don't have to do any method dispatch at all, right? Because now I freeze the type along that iteration of the loop. So I'm doing, type specialization on loops. And that's how we got this enormous speed up. On average, even the first prototype did 7x speed up over the interpreter. And that's very rare that you get that much of a speed up for a compiler optimization, right? And so we have these trace trees, and the trace trees keep growing, right? It's every time the model keeps growing, and every time we have a bailout, we just add. And we can't actually eliminate blocks because we might need them on additional, in the model, we keep adding. For the implementations, we may then eliminate code that's dead on that specific type specialized version of the loop. So we generate loop iterations for every different type receiver. And initially, we actually thought that our compiler would just keep adding loop bodies, as we discover them incrementally. It turns out that it's probably not the best way of doing things, because very many programs have phase changes. So after a while, we actually decided to stop adding things to our model after we've added a few branches. And if we still have bailouts, we actually throw away the whole model and build a new model. And with that, you can automatically even detect phase changes in the program and react to them very efficiently. So of course, there's pathological cases, right? So first of all, you can just have many equally lukewarm paths, right? And just by chance, you compile some of them and not the others. And that leads to a total code explosion in this case. And you also have interesting things. So up here, I have a loop, and the loop includes two other loops. And what happens there is that when you start tracing, you may very often not get back to the loop header because you get lost in one of the other two loops. So your trace recorder keeps, So these are all things that our original trace compiler could not handle at all, but that we later on managed to handle. So the original, the later compiler actually, and I think it's simple enough to see, right? So if the compiler knows all the things that could be potential loop headers, what you do is you actually at runtime dynamically refactor the binary in such a way that you actually turn loops into first-class runtime objects. And so the latest version of our trace compiler essentially restructures the program into just transitions between loops. And the things that the programmer has actually written, those things don't even exist anymore. So method boundaries completely disappear at runtime because every method is inlined somewhere and becomes part of some loop. So just to give you a final idea of how this actually looks. So this is a small JavaScript program, but actually you see this it looks really, really awesome what happens here. 35 method call, 129 guards, 224 total instructions for doing not very much. And when you optimize it, it goes down to 10 instructions and 2 loop guards, and that's it. So that's not so bad. So I'm already at the end. I've spoken very fast. So it's been interesting, right? So as I said, I saw myself for the longest time as actually being in the business of doing wire formats, and just-in-time compilation was kind of just an afterthought of this. I'm exaggerating, but the original idea was code mobility in some way. And I've sort of come around to the understanding that maybe sending source code around is really not such a bad idea after all. And the main reason why people didn't want to do that in the back old days is probably that they were afraid that people would reverse engineer their code. And today, decompilers are so good that there's not much difference whether you send around binary code or you send around source code. At least, and if you really want to, you can obfuscate both of these things, right? There is obfuscators for JavaScript as well. And if you really don't like either of this, you can still use WebAssembly and send a WebAssembly blob for your legacy code. On the other hand, the whole on-the-fly, just-in-time compilation thing has been really great, and because of the competition between browsers that has been fierce, there has been super great research happening in making just-in-time compilers better. Right? This would not have happened without the browser wars. The browser wars were really useful in getting all this energy focused on getting better JITs. And so today we are shipping these insanely large JavaScripts around, and people don't even notice, right? So that's absolutely great that you can send really large programs as source code to someone. If someone had told me that 20 years ago, I would have thought they're crazy, right? So, but it's routinely done today, and it just works, right? And there's far fewer problems with the source code approach than there ever was with Java and verification and all that. And so finally, I would want to thank a few people. So Peter Deutsch and Alois Schiffman, who have actually never met and never corresponded with, but without their inspiration, I would not have started this. Niklas Wirth for letting me do my thing. So I never ever published even a single paper with my advisor. So I think even he was not completely on board with this idea of doing code compilation on the fly. I don't think there's so many people who've never published a paper with their advisor and graduated. So Brendan, who basically bet the farm on this at the moment it happened. Andreas Gar, who was the student who originally did this with me and who is also on the patent. I actually graduated 34 students, and I've had lots of great students that have made it fun. And then you see, for allowing it to be given away for free, which is not entirely automatic. You have administrators don't have the same ideas as faculty sometimes at universities. And finally, the people who nominated me for this award and the committee who decided to give it to me, ACM and Microsoft, for paying for it. Thank you very much.